Every machine learning model has strengths. But what if one of the simplest models could become one of the most powerful? How do systems like Random Forest and XGBoost consistently outperform a single decision tree? The answer begins with one simple idea. Instead of relying on one model, why not combine many? The story begins with a simple problem. Suppose you want to predict whether you can go skiing. The answer depends on the time of year and where you are in the world. A straight line can't easily separate all those possibilities. Researchers needed a different approach. Instead of drawing one decision boundary, what if the model simply kept asking questions? Is the latitude greater than this value? Is the month before March? Every question splits the data into smaller groups. Then each group is split again, step by step, until the model reaches a final decision. That's a decision tree. Rather than learning one complicated equation, it learns a sequence of simple yes or no questions. But this creates a new challenge. Which question should the tree ask first? Researchers discovered that good questions create the purest possible groups. To measure that purity, decision trees use metrics like cross-entropy or Gini impurity. The best question is the one that separates the data most effectively. Then the process repeats, again and again, until the tree reaches its final prediction. Decision trees have several advantages. They're easy to understand, easy to visualize, and they naturally handle both numerical and categorical data. But they also have a major weakness. If they keep growing, they eventually memorize the training data. Instead of learning patterns, they learn noise. Researchers solve this by limiting the depth of the tree, stopping when leaves become too small, or by pruning away unnecessary branches after the tree has been built. Even then, another problem remains. Decision trees have high variance. A small change in the training data can produce a completely different tree. So researchers asked a new question. What if we trained many different trees instead of one? That idea became bagging. The process is surprisingly simple. Create many random versions of the training dataset using Bootstrap Sampling. Train a separate decision tree on each one. Then combine all of their predictions. Each tree makes different mistakes, but together, those mistakes begin to cancel out. The result is a model that's far more stable than any single decision tree. This idea evolved into random forests. Instead of allowing every tree to examine every feature, random forests force each split to consider only a random subset of features. That makes every tree a little different, reducing correlation between them and improving performance even further. But researchers didn't stop there. Instead of training many trees independently, what if each new tree focused on correcting the mistakes made by the previous ones? That idea became boosting. Each new tree pays more attention to the examples earlier trees struggled with. Over time, the model becomes stronger and stronger. This simple idea led to algorithms like AdaBoost and eventually XGBoost, one of the most successful machine learning algorithms ever created. And that's the journey. Start with a simple decision tree. Learn by asking a sequence of questions. Reduce overfitting through pruning. Combine many trees with bagging. Improve them further with random forests. And build increasingly powerful models through boosting. What began as one simple tree eventually became one of the most powerful families of algorithms in machine learning. But researchers soon began asking an even bigger question. What if we didn't have to hand design features at all? What if a model could learn its own representations directly from data? Inspired by the way neurons work in the human brain? That idea sparked the deep learning revolution. And it all begins with one simple building block: the neural network. And that's exactly what we'll explore in the next video.